Okay, so here we have an example of a continuous charge distribution. So the charge is smeared out over some region. And here it's a uniform line charge with density lambda. And they want to know what's the electric field above the midpoint at this point P here, and that's some distance D above the midpoint. Now notice they don't tell us how long the rod is. They just give us this angle, theta naught, from the midpoint to the edge, which is just a different way of telling us how long the rod is. But because that's the way they give it to us, we'll want to put everything in terms of some angle theta that will sweep along the rod. Okay, and we'll have to work out how to do that as we do it. Okay, so the idea is we're going to use Coulomb's law just like we always do. Coulomb's law only applies to point charges, so we need to make some point charges. This uniform line is made up of a bunch of little tiny point charges. Each one has some little tiny bit of charge dq. Each one of these charges dq creates an electric field which points radially away from that charge, and we can write the magnitude of the electric field from that particular charge. It's just Coulomb's law, and we're experts at that. So once we have the electric field for one of the point charges, the strategy is we make a bunch more point charges, and they all also have electric fields. And the strategy is you take all of their individual electric fields and you add them up. In the case of a continuous charge distribution, adding means integrating. Now, notice I've gone ahead and I've put the vector on this time. It's very important because electric field is a vector, and we have to sum the vector electric fields. We have to sum those arrows. And the problem there is the way you add vectors, you have to add components of vectors. So what we're actually going to do is, yes, we're going to find the magnitude of the electric field, but after we do that, in order to make it usable so that we can add it, we're actually going to try and find EX and EY, and it's actually those things that will add up, that will end up adding up at the end of the day. So let's go back to one charge and see how this works. Okay, so here I am. I have the one charge. This charge has a charge per unit length lambda, and it's got a length dx, some tiny infinitesimal length. So that's its charge per unit length times length. Now we said we don't want to use x as our parameter, so we need to somehow figure out how to write this in terms of theta. But that's actually not too bad because you've got a right triangle, and so the tangent of theta is x over d. So x is d tan theta, and dx is d secant squared theta. So the derivative of tangent is secant squared, okay? So that lets us express dq in terms of theta instead of in terms of x. So I know this doesn't look particularly pretty right now, but the payoff will come when we actually do the integral. The integral is going to be really easy to do. Whereas if you've seen in other examples where x is the parameter, the integrals can be pretty ugly. Sometimes you have to look them up in tables because they've got square roots and stuff, or you have to use something like trig sub. You'll see this integral is actually going to be pretty easy to do. Okay, at any rate, so let's set this up and get to work. Remember that we are going to have to break this into x and y components. So that is going to look like this. So we can write out the actual magnitude of the electric field. So again, it's Coulomb's law. And here, all I'm doing is I'm plugging in dq, but it's just Coulomb's law, more or less. Okay. And the thing we need to do now is to find x and y components for this thing. Remember, we can't add them until we find x and y components. And so how do we find the x component? Well, the x component looks like dE times sine theta. Why? Well, if this angle's theta, this angle is also theta. And so the x component ends up looking like opposite. So that's why the x component goes like sine theta. And the y component will go like cosine theta because that's the adjacent side of the hypotenuse. The only other thing we need to do now is we need to get rid of r, because r obviously depends on theta. It's the hypotenuse of the triangle. Okay, so we can substitute in for r. R goes like d over cosine theta, and so if you sub it in, it looks kind of like a mess, but what you get is actually something really nice and simple. Okay, so that is the x component of that little tiny piece of charge, and all that's left to do at this point is to add up the x components of all of the little tiny pieces of charge, and so that means we're going to integrate. And so what are we doing? We're integrating from minus theta to positive theta. In other words, we start at one end of the bar, at minus theta naught, and we sweep over all the way to the other side of the bar to plus theta naught. If you do this integral, you'll find that it's 0. Of course, it has to be 0 because sine's an odd function, and odd functions are symmetric. So whatever area you find here, it's going to be negative the area over here. So of course you expect to get 0. On the other hand, you also expect to get 0 from this integral because if you think about it, look, all the charge over here is pushing in this direction and all the charge over here is pushing in this direction. So the x components should cancel. You'll be left with a y component though. So let's see what that looks like. For the y component, you get basically the same thing you got for the x component, except instead of having a sine, now you have a cosine. And if you carry out this integration, you get a little factor of 2 here because cosine is an even function. So however much you have on this half, you can double it and you get it on the other half. So that's where that factor comes from. So that's it. That is the electric field. You found EX, you found EY. If you wanted to say specifically what the electric field is, you could say something like the electric field equals 0, 2k lambda sine theta naught divided by d. That's your electric field. An interesting question to ask is, what happens if this thing gets really, really long, right? Well, we already know that they tell us that the angle is theta naught. What happens to theta naught if this thing gets really long? Well, the length it is now, this is theta naught. You can imagine if we made it longer, theta would become a bigger angle. And if we make it infinitely long, well, then this angle theta is going to be like pi over 2, right? So if we want to know for infinitely long, we just set theta naught equal pi over 2, and we can say that the electric field in the y direction looks like 2k lambda over d, and then sine of pi over 2 is 1. So that's it. So that's the result you get by integrating. Later, in the next chapter, we're going to use something called Gauss's law, and we will get this exact same result using a completely different technique. All right, if you have any questions, feel free to ask.